All right, so let's start. So in the previous class, we were looking at these tail bounds for random variables. In particular, I derived the Chernoff bound, and we looked at some applications of the Chernoff bound to certain random variables. Right? The goal is always to derive the tightest possible bounds for probabilities of the form probability x greater than or equal to t for some t greater than 0, and probability that x is less than or equal to t for some t which is strictly less than 0. Right, so this is what we call the right tail, and this is what we call the left tail. So throughout we'll assume that x is the zero mean random variable, right? Because even if it is not a zero mean random variable, I can always look at x minus mu, which now becomes a zero mean random variable. So the Chernoff bound in itself is pretty hard to compute in general, right? Because it in fact gives us a family of bounds, but then you can optimize over the lambda over here to get the best possible tail bound. And we evaluated this for some random variables, particularly the Gaussian and the Bernoulli random variables. So in the case of the Gaussian random variable, we saw that the probability that x is greater than or equal to t is less than or equal to e to the negative t square by 2 sigma square, right? So the exponential, the tail bound takes the form e to the negative t square times some particular constant, correct? And we also saw that for Bernoulli random variables as well, we got a rather complicated expression in terms of the KL divergence, but then we could eventually simplify it to again get a similar tail bound, right? So the probability that x is greater than or equal to t is in fact, you can show that it is less than or equal to some constant times t square. Okay, and you can generalize this to even tail bounds for the empirical average 1 by n summation I equal to 1 to n of xi. The probability that this is greater than or equal to some t is less than or equal to e to the minus n times some constant times t square. Right, so this is the tightest possible tail bounds that we'll generally hope to expect. But the common feature between the Bernoulli random variable and the Gaussian random variable is that the dependence on t is e to the minus t square, right? In this case, probability that whatever x is greater than or equal to delta is less than or equal to some constant e to the minus some constant times delta square. And similarly for the Gaussian, it was this is less than or equal to 2 to the minus some constant times t square. Correct? So this corresponds to a class of random variables, what we call Subgaussian random variables. Both of them happen to belong to the same family. So remember that if x is Gaussian, then we derive the log moment generating function. So the log e to the lambda x, which we call psi x of lambda, this was equal to lambda square sigma square divided by 2, right? And because this is equal, this takes this particular form, some constant times lambda square, when we optimize over all possible lambda, we get a tail bound for probability absolute value of x greater than or equal to t. This turns out to be less than or equal to 2 times e to the minus t square by 2 sigma square. All right, so this is what we've seen so far. So we'll say that a random variable is sub-Gaussian if the log moment generating function is less than or equal to some constant times lambda square. Right? If the log moment generating function is basically a quadratic function of lambda, or upper bounded by some quadratic function of lambda, we'll say that the random variable is sub-Gaussian. And the constant that we have over here is what we call the variance factor, right? Any questions so far? Right. So this is just definition. So we'll go over this one by one. What are the consequences of a variable being Subgaussian, and why do we call this the variance factor? Right. So let's suppose that the log moment generating function is in fact less than or equal to e to the lambda square nu square by 2. So this simply means that the moment generating function e to the lambda x is less than or equal to e to the lambda square v square divided by 2. Right? So it turns out that if this is true, right, if expectation of e to the lambda x is less than or equal to e to the lambda square v square by 2, then the variance of x turns out to be less than or equal to v square. Okay, we'll see why this is true. So if a random variable is Subgaussian with a variance factor v square, then we'll say that x is in G of v square. So it belongs to the family of Subgaussian random variables with variance factor v square. Okay, so let's try to go ahead and prove this particular fact. Now, all we are given is that the moment generating function is upper bounded by some particular quantity, right? Expectation e to the lambda x is less than or equal to e to the lambda square v square divided by 2. So what would be your guess? How do you think we could prove this from this particular state?
We can compare to the value of Gaussian.
We can do what?
We can compare to the moment generating function of the Gaussian.
Okay. So we know that this is the moment generating function of a Gaussian. A Gaussian with mean 0 and variance v square, right? So how do you get the variance from the moment generating function? You can take the second derivative, right? But in fact, we'll try to do something slightly simpler. Let's just expand this term out. Okay. What would this be equal to? Expectation of, what would this be? So 1 plus lambda x plus lambda square x square divided by 2 factorial plus lambda cube x cube by 3 factorial and so on. Correct? So this is true for the left hand side. Okay. So let me say that the random variable that on the right hand side is z. Okay. So the right hand side is expectation of e to the lambda times z, where z is a Gaussian random variable with mean 0 and variance v square. So this is less than or equal to expectation over z of 1 plus lambda z plus lambda square z square by 2 factorial and so on. Right? And this is true for every lambda greater than 0. Right? Now, this is equal to, right? So this means 1 plus lambda times expected value of x plus lambda square expectation x square divided by 2 factorial plus lambda cube expectation of x cubed divided by 3 factorial on is less than or equal to 1 plus lambda times expectation z plus lambda square expectation z square by 2 factorial plus lambda cube expectation z cube by 3 factorial and so on. Now I have 1 on both sides, so I can just cancel these. What can I say about these terms? Lambda times expectation of x. What is expectation of x? 0, right? We are assuming that all random variables are 0 mean. So this is equal to 0. This is also equal to 0. And then I have a bunch of terms. So let me divide both sides by lambda square. Okay. So the left hand side is lambda square, and let me also set lambda to be equal to 0. So the remaining terms are whatever, lambda cube, lambda to the 4, and so on. So what will happen to the remaining terms? They'll all be equal to 0. Right? So if I divide both sides by lambda square, then I get expected value of x square by 2 factorial is less than or equal to expected value of z square by 2 factorial. Right? Which just gives me expectation x square is less than or equal to expectation of z square, or the variance of x is less than or equal to b square. Correct. So I'm not taking expectation of e raised to lambda x, right? I'm taking expectation of e raised to lambda x divided by lambda square.
Like when you are dividing by lambda square, like you have taken the assumption that lambda is not equal to 0.
That's okay, but I can also take the limit as lambda tends to 0, right? So effectively what I'm doing is that, right? So it's true for, okay, so firstly this statement is true for all lambda greater than or equal to 0, right? Because right hand side becomes trivially equal to 1. The left hand side is also equal to 1, right? So it's true for lambda greater than or equal to 0. But even if it were true that it's only valid for lambda strictly greater than 0, I have the following quantity on the left and I have a quantity on the right. I can as well take the limit as lambda tends to 0 on both sides, because it's valid for all lambda greater than 0. Right? So if you want to be more precise, let lambda tend to 0. Okay. Any other questions? Okay, so this sort of clarifies why I'm calling v square the variance factor, correct? But let's now see what are the consequences of a random variable being Subgaussian, or are there other equivalent characterizations for a random variable being Subgaussian? So suppose that I have a random variable which is with 0 mean, which is Subgaussian. Okay, then it turns out that all of these are equivalent conditions for Subgaussianity. So the definition that I gave was in terms of the log moment generating function, or the MGF. If the MGF is less than or equal to less than e to the some constant times lambda square, then I call it Subgaussian with certain variance factor, which effectively I have over here. So this is one definition of a Subgaussian random variable. But it turns out that all of these conditions are necessary and sufficient for a random variable to be Subgaussian. So we won't worry too much about the constant factor as long as it is different by some absolute constant. So if there's some universal constant sitting in between, I'll not particularly care about that. Okay, I'm not bothered about optimizing those constants. So this, as it turns out, as we know, if this is true, then the probability that absolute value of x greater than t is less than or equal to e to the minus t square by some constant, right? But it turns out that this is not just a consequence of the random variable being Subgaussian. It's also, you can also treat this as a definition of a Subgaussian random variable, because if this happens, then this is also true. Right? This should happen for all t greater than 0. Right? An equivalent condition is in terms of the moments. Right? So since we have a bound on the moment generating function, it's also true that we should have a bound on all the moments. If all the moments are bounded by some function, if the pth moment is bounded by some function of p, which is essentially similar to the moments of the corresponding Gaussian random variable, then the random variable is also Subgaussian. All right, but perhaps the not so obvious statement is that it's not just the bound. So we know that if the MGF is bounded from above by e to the constant times lambda square, then it is Subgaussian. But then you can also make a statement about the random variable x square, right? So if a random variable is Subgaussian, then the random variable of x square also turns out to be almost Subgaussian, right? So e to the expectation of e to the lambda square x square should also be less than or equal to e to the minus some constant times lambda square, but now in perhaps a limited range of lambda. Okay, and what this effectively means is that if I can derive a tail bound on a Subgaussian random variable, I can also derive a tail bound, a similar looking tail bound on the square of the random variable. Okay. But then this also, in fact, we don't even require something this strong. Even if the moment generating function of x square divided by some constant is bounded for some particular constant k4, then the random variable turns out to be Subgaussian. Yeah.
If x is Subgaussian, then x square is also Subgaussian.
It's not fully true, because I'm saying that this is bounded only in this particular picture. Okay. In particular, I'm not saying that the reverse is true. So, for example, these are equivalent conditions, right? If this is true, then this is also true, correct? So if x square is Subgaussian, then you can't guarantee that x is also Subgaussian. So these are both necessary and sufficient conditions. So for example, if x is Subgaussian, it does not mean that root x is also Subgaussian. Because if this were the case, that x is Subgaussian if and only if x square is Subgaussian, then it also means that x is Subgaussian if and only if square root of x is Subgaussian, if and only if the fourth root of x is Subgaussian, and so on. I'm not making that statement here. Okay. Any questions so far?
It will not be Subgaussian. It's lambda square only.
Correct. So on the left hand side, I have lambda square, but then you can also derive, in fact, derive bounds on e to the lambda x square if x is Subgaussian. Okay. Okay. So let's look at these statements one by one. Any questions?
That is one question.
Mhm.
Then the third equation will be true for all lambda.
All lambda, yes. Well, not exactly the third equation, because expectation e to the lambda x square would be less than or
So
equal
like
to.
we consider it instead of the lambda square, if we consider it then lambda, then
Okay.
like the
Correct.
right hand side would change, right?
Correct.
And it would be true for all lambda.
Correct. Yes.
belongs to R.
Yes.
So that would imply that this equation is also
Which equation is also
the
true?
third equation.
I'm sorry, I don't follow what you mean.
If x square is a Subgaussian,
Okay.
then the equation for that won't it imply that the third equation is also true? Because this range is a sub range for that.
Correct.
So if x square is a Gaussian, this implies this, and this end of it are equivalent equation.
But again, for x square to be Subgaussian, expectation of e to the lambda x square would have to be less than or equal to e to the k3 square lambda square. Right? Okay, sure. So I'm saying that expectation of e to the lambda square x square is less than or equal to e to the k3 square lambda square. Right? This as a function of lambda is important. So for example, if I were just to replace lambda square by lambda, right, or some rho, this says that expectation e to the rho x square for rho less than or equal to some particular constant is less than or equal to e to the constant times rho. Correct? Not rho square. That doesn't mean that x square is Subgaussian. That turns out to be slightly weaker than Subgaussian, and that's something we'll explore next. Okay. Okay. So now that we have this, let's prove these statements. Okay. So suppose that this is true, right? So probability. Let's try to prove that the first statement implies the second statement. Probability that absolute value of x is greater than t is less than or equal to e to the minus t square divided by some constant. Using this, I want to derive a bound on the pth moment of x. Okay, how would we do this? Okay, so this requires an alternate expression for the mean of a random variable. I'm not sure if you've seen it before, but it's an interesting result. So suppose that y is a non-negative random variable. Right? And expectation of y equals to some mu. Then you can write mu as the integral from 0 to infinity probability that x is greater than t. Sorry. Y is greater than t dt. Have you seen this before? Okay, so I leave this as an exercise, but maybe give you a hint. What is the expression for the mean of the random variable of, let's say, a non-negative random variable? It's integral 0 to infinity x times the density of x dx, right? Yeah. Sure. Correct. So that would be the CDF. Agreed. And well, you can get it using a similar approach, but basically you have x. You can write x itself as an integral, as let's say integral t from 0 to x dt, right? If you just take that and change the order of integration, it turns out that you'll get this. Okay, so I leave that as an exercise. Okay, so now let's say that we have this. Then what is expectation of absolute value of x to the p? This would simply be integrals from 0 to infinity, probability that x to the p is greater than t dt. Okay. Okay, what do you think we should do next? Remember, I have a tail bound on probability that x is greater than t.
Probability of mod x being greater than equal.
Okay, so let's do that. So integral from 0 to infinity, probability that mod x is greater than e to the 1 by p dt. What next? Take this less than or equal to e to the minus t to the 2 by p divided by k square, let's say k1 square dt.
There will be a multiple of two.
Sorry?
There will be a multiple of two.
There will be, correct, this is multiple. What can I do next? T to the 2 by p. Can I do a change of variable? What change of variable should I take? Let me take t to the 2 by p equal to some y. So what is dy equal to? T to the 2 by p minus 1 times 2 by p dt, right? Or in other words, what is dt equal to? So p by 2 times, yeah, correct. So it's divided by, or t to the 1 minus 2 by p times dy, which in terms of y to the p by 2 minus 1 dy. Correct. So let me plug this in there. So I have expectation of mod x to the p is less than or equal to integral from 0 to infinity p by 2 y to the p by 2 minus 1 times e to the minus y dy. There's another divided by k1 square. Okay, so maybe I should have done this differently. Let me say divided by k1 square, so that this is equal to this divided by k1 square so I have t to the 1 minus p, but t is y times k1 square, or t to the 2 by p is y times k1 square. So this would be equal to k1 square whole to the p by 2 minus 1, right? Which is p by 2 k1 square raised to the p by 2 y to the p by 2 minus 1 dy. K1 to the, correct? Okay, so this, let me take all the constants outside. I have p times k1 to the p integral 0 to infinity y to the p by 2 minus 1 e to the minus y dy. Right? But have you seen this integral before? This is gamma p by 2. Right? And do you know of any bound on gamma p by 2 from your first exercise? Yeah? It is? Correct. So in other words, I can just bound this by p times k1 to the p times some constant, some universal constant, times p by 2 whole raised to p by 2. Correct? So this is, if I take sort of root p, this is gamma p by 2. This would be p by 2 minus 1. So this would effectively be k1 times root p whole raised to, yeah? I'm just taking that along with this, right? So this universal constant takes care of all of those things. It can be any constant factor. That's why that is exactly why I said I'm not going to be concerned about how large the constant factors are. They're at most going to be like 10 or 15 or something, not more than that. So this is some constant times k1 times root p whole raised to the p. Okay, and this is true for any p greater than or equal to 1. Any questions? Okay, so now let's try to prove the third statement from the second statement. Right? So if I'm able to prove that the second statement implies the third statement, then it also implies that the first statement implies the third statement. Okay? So I know that expectation of x to the p is less than or equal to some k2 root p whole raised to the p. Okay, so and I want a bound on expectation e to the lambda square x square. Okay, so now what do I do? Yeah, put p equals to y. Okay, but I want expectation e to the lambda square x square. Right? Great, so let me do that. I'll just expand I'll write the Taylor series expansion of e to the lambda square x square. So this is summation I equal to 0 to infinity, expected value of lambda square x square whole to the I divided by I factor. Correct? Okay, but this is just summation I equal to 0 to infinity lambda to the 2i expected value of x to the 2i divided by I factor. Right? But I already have a bound on expectation of x to the 2i. Right? Because expectation x to the 2i is also equal to expectation of mod x to the 2i. So this is less than or equal to summation I equal to 0 to infinity lambda to the 2i k2 square root of I whole raised to 2i. Should be a 2i. Divided by I factorial. Right? Now what do you think I could do? Sorry. Yeah. Okay, so let's try to do that. Let me just... Sorry?
Write K2
Okay,
not equal to some K3.
that's okay. We'll think about that later.
That would directly imply the
That would directly imply the right hand side. So this is less than or equal to summation I equal to 0 to infinity. Let me perhaps merge k2 root 2 along with this lambda, right? So lambda times k2 root 2 whole to the 2i. What do I have left? I have I to the 2i divided by I to the I divided by I factorial, correct? How do I work with this quantity? Yeah. Of what? What do you mean Taylor's approximation of Stirling's approximation of I factorial? So that's again less than or equal. This is, I can write that this is less than or equal to summation I equal to 0 to infinity. So I factorial is I raised to the I divided by some constant raised to the I. So I have some lambda times some other constant times k2 whole raised to the 2i, and I raised to I and I raised to I just get cancelled. Right, I'm just using Stirling's approximation. Okay, now what do I do with this? This is a geometric series, right? So this is less than or equal to 1 by 1 minus lambda c k2 for as long as the absolute value of lambda is less than or equal to strictly less than 1 over ck2, right? As long as this quantity is, or lambda ck2 square whole square is less than 1, this series converges. Correct? So it's less than or equal to 1 over 1 minus lambda ck2. What can I do next? Yep. Correct. That's right. So it turns out that for small enough x, one by 1 minus x is less than or equal to e to the minus e to the 2x. Okay, I want an exponential bound, and for sufficiently small x, this is less than or equal to e to the 2x. So expectation of e to the lambda square x square is less than or equal to e to the 2 times lambda ck2 the whole square, but only if lambda ck2 absolute value is less than half. All right. So this is less than or equal to e to the lambda square a3 square for lambda lying in a certain range. Okay. Now 3 to 4 is straightforward, because if this is less than or equal to this, then obviously this is less than or equal to 2 for some constant k3, right? So if this is true, so suppose that expectation e to the lambda square x square is less than or equal to e to the lambda square k3 square, I can choose a lambda such that this is less than 2, right? For example, I could just take lambda to be equal to 1 over k3 square, or something slightly smaller than 1 over k3 square, because this has to be strictly less than some constant, right? So okay. Now for the next step, I'll try to prove that the third statement implies the fifth statement. Right, so I have a bound on expectation e to the lambda square x square. So this is less than or equal to e to the some k4 square lambda square for k3. Suppose that this is true. I want to show that this random variable is Subgaussian. So in other words, expectation of e to the lambda x is less than or equal to some e to the some constant times lambda square. Now again, for this I'll use some trickery. Essentially, I'll use the following inequality, that e to the x is less than or equal to x plus e to the x square. Okay, again, for now I'm using all of this without proof, but you can prove all of this rigorously. So if this is true, then expectation of e to the lambda x is less than or equal to expectation of lambda x plus e to the lambda square x square. But what is expectation e to the lambda x? It's 0. And expectation of e to the lambda square x square is upper bounded by e to the k3 square lambda square. So this is less than or equal to e to the k3 square lambda square. But now there's a catch, right? Because expectation e to the lambda square x square is less than or equal to this only for lambda lying in a certain range. But I want something stronger. I want this bound to hold for all lambda in R. Correct? So what can I do about this? So suppose that whatever K3 lambda is greater than 1. So this is the regime of interest where I cannot simply use a bound on expectation lambda square x square. Right? So in this case, I can write 2 lambda x as less than or equal to lambda square by K3. K3 lambda square plus x square by K3 square. Why is this true? This holds for any real number x and any real number lambda. Sure. Or in other words, you could just think of if I take this to the right hand side, then it is simply K3 lambda minus x by K3 the whole square. Right? This is the same as saying 0 less than or equal to K3 lambda minus x by K3 the whole square. Yeah. Okay. K3 square. This should also be K3 square. Okay, so now I want expectation of e to the lambda x. So this is less than or equal to expectation of e to the K3 square lambda square times e to the minus x square by 2 K3 square. I claim that this is less than or equal to e to the expectation e to the, okay, just e to the K3 square lambda square by 2 times expectation e to the minus x square by 2 K3 square. But what is this? What can I say about this particular quantity? Why is it less than 1? Why is it less than 1? Correct. This quantity is less than 1 for every value of x, right? So this is less than or equal to expected value of 1, which is 1. Yeah. If I have, oh, that's Thanks for correcting that. That is it. It will be e to the plus x square by 2k3 square. But then do I have a bound for this quantity? From the previous. I have a bound on e to the lambda square x square for all lambda less than or equal to 1 over k3.
Because 1 over k3 is equal.
Correct. So this is less than or equal to some constant times e to the k3 square lambda square, some k4 square lambda square, right? For some constant k4. Okay? So I know I'm out of time, so maybe we can stop here. We'll again quickly go through this once again in the next class.